Hey, it's time. Welcome back, everyone. So we're back in our normal classroom. We have our normal projector. And just before I forget, because it's a brand new projector, please let me know at any time if things just look distorted, not zoomed in enough, or anything along those lines, whether you're here in class today, in person or in Zoom. But otherwise, I don't have a whole lot of announcements to give. Let me close this. We're on our penultimate section, section 6.6. 6.7 will be the final section for the entire course. And pretty much what we're doing in both of these sections is just pure equation solving. 6.6 doesn't have a lot of context. These are just mostly equations. And 6.7 does. These are applied problems, but we're still solving the same kinds of equations. We just have to set up some of them to get started on that section. So 6.6, 6.7 are very, very good to go together, I would say. We'll probably finish section 6.7 and start it on Tuesday of next week. So we're not trying to rush through both of them. And we'll have a review on 1 week from today. Also, quiz number 13 down below. This one is the final quiz. This one is kind of an oddball. I have to completely admit to you on this one. The math department just wants to see how we would perform on this quiz. And so they requested that we do a problem like this one. It's an applied problem where we have to find, let's see, the exercise yard will produce the maximum enclosed area. So go back to working with polynomials, use the vertex formula, and you can find the maximum. But just like all the other quizzes, if you have a question, don't hesitate to ask. I'll be very happy to help out. But that's the final quiz. So again, congratulations. I think I'm saying that a lot, but we're just about there. Well, any other questions or comments, folks, before we get started today? Okay, let's jump in. So a lot of the work that we've been doing all along in chapter 6 and some of it in chapter 5 was so we can solve these equations here and the applied ones in section 6.7 as well. Let me move this over. It's not cooperating. Hang on. It's usually a little bit easier to work with. There we go. And here's what the notes look like. I would say example 1, this one's kind of a warm-up, but it's possible that this would be a type of equation, either A and B on the final exam, but they're also on the homework and Alex. So I figured we ought to start here just as a starting point. To solve these kinds of equations, we could use logarithms and it would absolutely work on them. But if there's an easier way, and the equivalence property of exponential expressions, that is the easier way, we ought to give it a try and see how it goes. First thing we need is a valid base. It has to be positive, not equal to 1. Then the property reads, if b to the x equals b to the y, then that statement is true if and only if x equals y. So if you have the same base raised to powers, the powers themselves must be equal. Any questions about that property so far? Okay. For just a really fast example before we look at part A and B, you could say, for example, if the equation goes e to the x equals e power 4, then this is only true if and only if x itself has to be 4. So that's pretty much the property in action. But you're usually going to use it if you see part A and B right here. The goal is to get a common base so that we can equate the exponents. So in part A, we have a base of 7 to work with. 1/49. If we can write that as a base 7, then we'll be all set. So let's start by taking this portion, go up to the margin, and start working with 1/49. First thing you would want to do is definitely factor this. 49 is the same as 7 squared. That 7 is in the denominator. Let me fix that real quick. Now that we have 7 squared, we're looking at the same base almost. We just need to promote base 7 up to the numerator. When we bring it up to the numerator, the power changes to a -2. And that's pretty much the main trick on this problem so far. So this portion, 7 to the power -2, is just going to replace the 1/49. Any questions at all, folks, to that stage? Okay, so next step, I'm just copying the left-hand side for the moment. 7 to the power 2x minus 3 is equal to, right here we can put in the substitution. 7 to the power of -2 goes where 1/49 was. And we have power x plus 1. Now it's still not quite to the property we want. The equivalence property requires we have a base b to a power. We have the base 7 to a power -2 times another power. So it's probably a good idea to take just one additional step. This becomes 7 to the power of 2x minus 3 equals, let me write this in as now 7 to the power. Here's our new trick. This -2 as an exponent will multiply the x plus 1 as an exponent as well. So it'll turn into -2 times x plus 1. Now, this is finally where the equivalence property works. We have a base 7 on the left, base 7 on the right. And the only way that's possibly true is if the exponents themselves are equal, much like what happened on the upper right margin here with that simpler example. So from here, here's the major step. We can say this implies 2x minus 3 is equal to -2 x plus 1. So we took an equation that was an exponential equation with exponential functions on both sides. It's not nice to look at. But if you do the right steps, it just turns into an ordinary linear equation. Any questions or comments, folks, before we finish this one off? Okay, let's go through the motions. We'll keep the left-hand side the same, 2x minus 3. On the right-hand side, distribute -2 to get -2x minus 2. At this stage, we want x's on both sides, so let's add 2x to both sides. That'll give us a 4x minus 3 equals -2. So I've consolidated x to the left-hand side. Next, add 3 to both sides. 4x will be positive 1. Divide by 4. And here's the solution. The only possible way this original equation was true is if x itself comes out as 1/4. So we did it, folks. We solved our first exponential equation. We've actually solved a couple of these, but first one for the notes at least. Well, any questions or comments, folks, on the strategy here? Okay, it's a nice strategy, but honestly, this one's kind of a trick that sometimes it works out really well. Other times we have to use logarithms to solve these kinds of equations because it's not always easy to get the same base, say 7, on both sides of the equation. Here, well, I think we can make this happen. We have 16, which is a power of 2. 4 is a power of 2. But we could do even better because 16 is also 4 squared. So it's probably easier to go with the simplest maneuver here. Instead of writing 4 as 2 to the power 2, let's just write that 16 as 4 to the power 2. But we'll get our common base much, much faster that way. And that means we're doing the least amount of work. Well, let's then start with left-hand side. 16 here can be rewritten as 4 to the power of 2. The exponent is still a 1 minus x. And the right-hand side, I'm just copying in 4 to the power of x squared plus 8x plus 11. At this stage, we're just about done, but let me make that power 2 a little bit bigger. But it's well worth it to take one additional step. On the left, write this in as 4 to the power of 2 times 1 minus x. So once again, the exponent here and here, they just have to multiply in this configuration. Then the right-hand side is 4 to the power of x squared plus 8x plus 11. So now we have the same base. With equality in the middle, the only way this equation is true is if the exponent on the left, exponent on the right are identical. So we're going to just grab those two, set them equal to each other, and that's the last steps on this one. 2 times, let me move it up to the right here, 2 times 1 minus x is now x squared plus 8x's plus 11. This one's not as nice. Once we went to this format, we don't have the linear equation like in part A. That's now a quadratic equation. If you see a power 2, the strategy is now get 0 on one side and start factoring or using the quadratic formula. We can begin by, say, distribute the 2 in. It's 2 minus 2x equals x squared plus 8x plus 11. The next thing, let's see here. I'll subtract 2 and add 2x. let me write that in as a step just to more clearly show that. That's a multiple step operation. So add 2x to both sides. Subtract 2 from both sides. Here's just a quick tally bar, and we get 0 equals x squared plus 10x plus 9. So that's our quadratic equation to solve. And you could hit it with a quadratic formula. There's no harm in doing that. But if you see a faster way, it's always good to take the simpler strategy. This one looks like it factors, so let's just factor it. 0 would be equal to 2 groups multiplying. X and X would go in. Because of positive right here by the red dot, the inner signs have to both be the same. And because of this positive, it tells us they're both positive, in fact. So plus and plus. And with this 9 here, you could try 3 times 3, but those would add up to a 6x. We go with a 9 and a 1. Folding this out, we'll return the 10x in the middle. So that's our correct factorization. So let's take a look at what the process was. It started out as an exponential equation. We broke it down to a quadratic equation, but the moment you factor it, it becomes linear. There's just 2 linear equations. X plus 9 equals 0, or x plus 1 equals 0. And this is really common in mathematics, where we take an equation that's nasty, like the original one, and our methods are just to try to break it down into something familiar, like a quadratic equation, or even better, 2 linear equations is where we want to be to solve this thing. We can immediately, in one step, write x equals -9 or a -1 for the solution on this one. So we did it, folks. That's the full method on getting through that equation right here. Any questions or comments at the moment? Okay, these ones again are kind of special equations. They just worked out. It was rigged to come out right. And one way it would have been a really bad equation is if this, I'm going to fix it in a moment. If this was a 5, I'm in really, really bad trouble because I don't see an easy way to write 16 as a power of 5. There's just a huge mismatch on this one. So whenever that happens, what we need are logarithms to start solving everything here. So that's going to be our next set of equations. But first, any questions or comments, folks, on the strategies so far? Okay. Let's bring up the next thing we're going to be working on. For the equations we're about to solve, Alex has a common thing that it's asking for. It's going to ask sometimes for just the exact answer. Sometimes it wants a decimal approximation. Sometimes it wants both. So when I wrote the notes, I wrote it so that we'll do pretty much both. Let's find exact answers and also approximate them so we can get practice on both ends of that process. So for your calculator, TI-30X2S is a good choice. If you like the TI-30XA, that's still a great choice as well. The buttons you're going to be wanting to work with are pretty much the natural log button, but no harm with log base 10 if you prefer that one as well. And here's our new set of equations. It says solve the equations, give an exact answer as well as an approximation, and we'll go for 2 decimal places of accuracy. Well, any questions, folks, before we try this new batch? Okay, this one's really rough, and let's take a look at this right here. If that 3 was a 2, it'd have been a fast equation. Exactly. We just need to use logarithms to solve this thing right here. So because of the 3 and the 8, our strategy above is not going to work. And like you said, logarithms are a really good choice on this one. So coming down below, I like that you said use log base 3. That's a great approach. It gives you an exact answer as fast as possible. But if you use log base 3, you will also have to use the change of base formula when you go to give the decimal approximation. So what I would propose for these kinds of problems, the natural log is a really great function. It's fast to write. You won't need the change of base later on when you go to approximate your answer. And so my strategy is for these, I'm going to hit them with the natural log. You don't have to do it that way. There is lots of ways to solve this. But I think that's a decent approach for getting the approximation as well. So there's our equation, 3 to the power of x equals 8. First thing you want to do is take the natural logarithm of both sides. Natural log 3x equals natural log 8. Now, this is a moment of truth. We have to ask ourselves, in what way does this actually help us? Anyone see what the next step would be? Well, this is a good reminder as well that what we really need here are properties of logarithms. For using logarithms to help solve the equations, we need those properties. So let's go back to the course page 6.5. And the stuff we want is this right here, scrolled right past it. Let me just take a quick screenshot and let's throw it in the notes. I'll just take this portion right here. And we'll copy this down as we go to solve out all these equations. So now that we have properties of logarithms, turns out the property that we want the most is property number 7. We have a power, P. The power is playing the role of X from right up here. But we would rather X is not in that location if we're trying to solve it. And what it allows us to do is take that and put it in front as a coefficient. So in our problem, this X is going to move right there in the very next step. We'll get X natural log 3 equals the natural log of 8. So that is the critical step which we needed properties of logarithms for. Does that make sense, folks, on using property 7? Okay, so again, the idea, whatever is here comes down as an exponent, and that's where it's going to emerge. Once we've done that operation, all we need to do is divide by natural log 3. Our work is done. X is going to be equal to natural log 8, divide by natural log 3. And if you did use log base 3 to start the equation and use the change of base formula, this is probably where you're going to end up. This one is the exact solution. X is exactly natural log 8 divided by natural log 3. And if we want to approximate it, we can write X approximately equal to and just shove that into a calculator. Before going to the calculator, any comments at the moment? Okay, as we calculate these things, interrupt me at any time if you're getting some weird different answer. That way we'll be in great shape and know that we're getting the same kind of stuff when we do them for real on a final exam. Let me open up a quick calculator. Usually that's a little bit easier to do, but there we go. I think we can work it like about there. That's as much as they're going to give us, it looks like. But we just take in natural log 8, divide by natural log 3, and this is our answer rounded to 2 decimal places, 1.89. So down below over here, 1.89 is our answer finally. I said finally, but I don't know if that's fair. This was actually a pretty quick solution to get through. Well, we did it, folks. Yeah, go ahead.
So, to get X, why are we divided by those 2?
Well, to get X alone, we had to divide by the natural log 3.
Oh, okay, gotcha. So we go to the other side.
Exactly. It just looks really abstract, right? Because we're just seeing so much stuff around there. But think of that as just a glorified number 3 itself. You're dividing by 3.
Just to get X by itself.
Exactly. Other questions so far? Okay, let's try it out again then. So part B here, really again, these equations are about the properties of logarithms, and we happen to be solving equations as well. And to get through this one, well, it almost looks like you would probably want to use property 2. But there's a problem with property number 2. Let me blow that up. The 2 that's right here by the red dot is blocking the cancellation. There's no 2 right in front of this formula right here. So what we need to do is first actually use this property, but going in reverse. We need to take this 2, get it out of there, and make it become a power on X. So the opposite of what we did over here. So if we make that happen, here's what the reward is going to be. It'll turn into e to the power of the natural log of x squared. is now equal to 5. So we're done with property number 7. Property number 2, if we wrote this out in a format that looks like log base e, it would have looked like this. Let me try again. E to the power of log base e of x equals x. Or you could say e to the power of natural log x equals x. So that's just a different way to visualize property number 2. So back up here, here's the whole punchline. That's gone, and all you get is x squared. Everything else is just wiped out. And that's the beauty of having an inverse function. It will allow for massive cancellations. Now, x squared equals 5 is all we have to solve. But before we get too excited, we should be really careful when we see natural log x in the equation to start. Let's put down a little warning over here. Because there was a natural log in the entire problem, natural log x has domain x greater than 0, or an interval notation, 0 to infinity. That means when you go to solve this equation, we need to be extra careful. We cannot pick up a negative solution. Our solutions cannot even be 0. They must be positive answers. And that means this is one of the weirdest problems ever, where if you knew taking the square root of both sides of an equation gave you this, then you now have to also throw away the negative solution to get full credit on this problem. It's kind of nasty in a certain sense. So here we'll say x equals root 5 is our answer. Let me box that since there's a lot of stuff here. And x equals negative root 5 is not a solution. Again, because x has to be positive, only because the natural log appeared in this equation. Well, we did it, folks. There's a second equation solved. This one, we didn't even have to apply a logarithm. We just used property number 2 to get through it. Any questions at all before we try out another one? Okay, let me clear this off for just a moment. And let's give part C next a try. Now, sometimes in ALEKS, there is a really big, I'd say, hint on some of these problems. Sometimes when you're solving equations, there's a little option that says no solution. Sometimes that could be a possibility. And if you see that, it means we should be extra suspicious about these kinds of equations. Now up here, natural log x had an extra technical issue. We couldn't pick up a negative solution due to its domain. And there's another big issue on part C. But let me write it down this way before we get started. The issue on this one is, we know from experience, if you graph any exponential function, say something of the form y equals 10 to the power 3x plus 4, or just even 10 to the power of x, doesn't matter really what's going on here. This is going to be bigger than 0 for all x. And we can visualize that. Let's graph this real quick just to see it happen. We take y equals 10 to the power 3x plus 4. There's our graph right here. It's definitely bigger than 0. We have to zoom in to see the separation from the x-axis on that. But this thing is always positive. That means we need to be cautious when we go to solve this thing. If we do the first ordinary step of subtract 83 from both sides, we get 10 to the power 3x plus 4 equals negative 51. And then already, right at this step, we have to stop. There is no solution because of this property right here. That deserves an exclamation mark because that's really kind of tricky. We're going to take a look at this in another way. I'm explaining why it has no solution by thinking of this as an algebraic property or considering the graph as never negative. But let's take a look at it from a different point of view as well. Suppose we didn't notice there's no solution and we were going to take another step on this thing. The extra step would be take the natural log of both sides. it would look like this. Natural log 10, 3x plus 4 equals the natural log of negative 51. And now we have another big problem. Recall, natural log has domain x bigger than 0. Even if you try to put negative 51 in your calculator, it's just going to tell you domain error or syntax error, anything along those kind of lines. So there's no solution for multiple reasons, and either way you detect it is equally valid, I'd say. You can't proceed by the logarithmic statement, and also the equation just doesn't even make sense. The graph of 10, 3x plus 4 is a positive graph. So watch out for those kinds of equations. Sometimes there's an equation where there's nothing to do but say no solution, like this one. Well, any questions at all, folks, with A, B, and C so far? Okay, let's try out then our next one, part D. And this one doesn't seem to have anything too fancy going on with it. It's a base 2, a base 15. If that was a base 16, we would have an easier way to solve this without using logarithms. But 2 and 15 are incompatible with bases. Easiest thing to do is, let's just take natural log of both sides to start. So first, natural log of 2x plus 4. Oh dear, sorry, some technical issues here. 2x plus 4 is now equal to the natural log of 15 to the power 8x. So that's our first step to get started. And the only reason we like the natural log is, well, it's easy to write. We're going to be effective when we go to give a decimal approximation. And property number 7 is now in effect. What property number 7 is going to do is take this right here. You know, it's a good call to actually put parentheses around this for the next upcoming step. And x plus 4 will be transferred into a coefficient. And then the 8x here, parentheses are not as vital since there's a one single term. This one will also become a coefficient as well. So that's our first step, just using property 7. Any questions, folks, so far? Okay, so here's what it looks like when we actually use a property 7. Arrows are just saying what we're about to do. X plus 4 is now a coefficient to the natural log of 2. Likewise, on the right-hand side, 8x is now multiplying natural log 15. And that's now a much, much friendlier equation to solve because x is no longer in the exponent. And that's what logarithms are really, really helpful for. Property 7 is a superstar here. And now we have to solve for x, and we have several problems. X is tied up in a group, and it's also on both sides of the equation. We can solve these one at a time. Maybe first step, let's free up x by distributing. This looks really weird because we're distributing natural log 2, but just recall natural log 2 is just as good of a number as 2 itself. If that was a 2, we would have gotten 2x plus 8. But if it's natural log 2 and you distribute, you'll get x times natural log 2 plus 4 times natural log 2. Does that make sense, visualizing that distribution there? Okay, to me, what's kind of tricky about this is it just looks abstract when you see natural log 2 there. And if you're not sure if it's the right step, always work by an analogy. The analogy would be you're just taking x plus 4 times 2, that's the normal thing, to get 2x plus 8. But here we were putting natural log 2 and natural log 2 here, and that's why it looks a little bit different, but same kind of process. On the right-hand side, nothing special happens. We don't have any cause to distribute. In fact, we can't. It's just 8x, natural log 15. And so now we've corrected one problem. X is freed up from the group. It's still on both sides of the equation, but that's not too terrible of a fix. We can subtract 8x natural log 15 from both sides to bring it on one side, subtract 4 natural log 2 to get just x's on that one side. So let me write out that step since that's a lot going on there. Subtract 4 natural log 2, then subtract 8x natural log 15 minus 8x natural log 15. Here's the big tally bar. Oh, that's not the enter key. There we go. And here's what we're going to get as a result. These are not like terms. We have to write them as x, natural log 2. Then from down below, minus 8x, natural log 2. Or excuse me, 15, minus 8x, natural log of 15. Over here, that's a cancellation in that column, so we'll skip to equality. These are also like terms, cancellation in that column, and we're just carrying down -4, natural log 2. So all I've done in this step is just rearrange the equation. We need x's on one side, then that's what we got, and we want only x's on one side. So to make that happen, factor x out of both sides, or both terms of this side. X factors out, and you're left with natural log 2 minus 8 times natural log of 15. Still equal to -4 natural log 2. So now at this stage, x is in one spot, and the only thing we have to do to solve it is divide by this entire group, natural log 2 minus 8 natural log 15. Probably a good moment to catch our breath on this one, though. Any questions so far? Okay, so let's make that step happen. The only thing remaining on the left is just x. On the right-hand side, it's -4, natural log 2, and a larger division bar than normal. And everything inside this group just is going now to that denominator. Natural log 2 minus 8, natural log 15. And you could use properties of logarithms to simplify this denominator a little bit, but I honestly feel like that's usually not really worth it. It's almost best to just leave your answer like that, give it to Alex, and then do the approximation here. So I'd say typically answers are just left in that format for these kinds of problems, and that's always completely appropriate. Any questions at all, folks, on getting the exact answer? Okay, all we have to now do is approximate that thing. So right here, x is approximately equal to, we're going for 2 decimal places. And this will be -4 natural log 2. We're dividing that whole thing by natural log 2 minus 8 natural log 15. And to 2 decimal places, this is a 0.13. We did it, folks. I would say part D is a pretty tricky equation. If you see something like this one in Alex, this might be a good place into the notes to come back to just for a refresher. And kind of what's going on here, the way we solve this equation, it should feel very similar to finding an inverse of a rational function. Whenever we did that, we had a variable, it was y, the 2 sides of the equation, we had to distribute, factor, then divide. It actually looks extremely similar. In fact, just to drive that point home, let's take a look at it for just a moment. I think we did that in 5.7 as well. And yeah, that's pretty much the process. If you're solving an equation like this, what you would first want to do is clear the denominator. Now you have your y on both sides of the equation. You can bring it to one side, then factor it out, then divide. Really, that's exactly the same thing as what we did over here, just different stuff that we're looking at. Well, that's a pretty difficult question now completed. What we're going to be doing now is looking at more different kinds of equations. These were all exponential in form. Next, we'll look at logarithmic type equations. Any questions, comments, concerns first before we take a look? Okay, it starts off kind of nice, I'd say. We have another equivalence property. So let me take this, just in case we'll need it later on. I think we probably will. Oh, it's already right here. So we'll leave that one in right where it is. So the equivalence property of logarithmic expressions, pretty much just like what we saw in the very top of the notes. If log base b of x is equal to log base b of y, then the only possible way that could happen is if x is y. What we require is the same base right here and right here. And then the inputs would have to be equated. And here's a really quick type of example along those lines. If you have natural log x equals natural log 3, on the surface, this looks like a really kind of esoteric equation, right? But natural log has the same base. It's base e here, base e there. And so x is 3. That's our conclusion. And the whole equation is now solved right at that step. So that's what we're going to take a look at in example 3. The trouble with the equivalence property of logarithms, much like this property above, is it just doesn't always work. When it does work, it's the best strategy to use. And when it breaks down, we have to do something else. But it hasn't broken down yet with these two examples here. So these are the examples where it will work. Double check you have the same base. This is log base 7, log base 7. So it matches here. And that means the input, 12 minus x, is equal to x plus 6. And that's pretty much our step on this. 12 minus x is x plus 6. Now, this is a really fast equation. We can add x to both sides to eliminate that negative x. 12 is 2x plus 6. Then subtract that 6. 6 is 2x. Then divide by that 2, it will get 3 equals x. Then our work is done. It's good to double check here to see if things work out, especially if your equations start off with logarithms. If you plug 3 here, you'd have log base 7 of 9. 3 here, log base 7 of 9, and that's a true statement. Log base 7 of 9 is equal to itself, certainly. So we did it, folks. That's a really fast equation to solve. Any questions at all getting through that one? Okay, same kind of deal here. This is natural log, so they both have the same base of e. Not sure what to highlight. I'll just highlight the whole thing. Why not? That means all of this has to be equated, and it follows that x squared plus 6x is now 7. So we're just equating the inputs to the logarithms. So if you have two logarithms and they're to the same exact base, this is always the best way to go. But now it's a quadratic equation, so we need 0 on one side. We've got an x squared plus 6x minus 7 is 0. Next thing we need to go for is a quick factorization. Let's go with the x and x. Automatically with the negative right here, we have to mix our signs. So we got to go plus and minus. If you see a prime number like 7, that's sometimes almost a freebie. We can put a 7 here, a 1 there, the only sensible factorization. And this would work. X times negative 1 gives us negative x. 7 times x is 7 x's. Those sum to the 6x in the middle, so we've got the right stuff. Next step, we've got two things multiplying resulting in 0, which means x plus 7 is 0, or x minus 1 is 0. And both of those equations are very easily solved. Here, subtract 7 for a solution of negative 7. Add 1 over here for a solution of positive 1. So we've got it, folks. Those are the solutions. Maybe. We definitely always want to check these out whenever we're dealing with logarithms. There can definitely be a possibility of extraneous solutions. So first, let's visualize plugging negative 7 here. We would have negative 7 squared plus 6 times negative 7. So if we plug in negative 7, we'll get natural log of 7, which is the right-hand side. So we're in good shape. We plug in 1 instead. Let's just throw it in there. That looks like it should work out. Yeah, we get 7. So 1 here is natural log 7, balancing the equation. So it looks like we keep both of the solutions here. Just because we have a negative doesn't mean we necessarily get rid of it as a solution. Well, any questions, folks, on these two equations here? Okay, so these are like the best case equations whenever logarithms are coming into play. But if you have a slight change to this, maybe the right-hand side was just a 7, or maybe there's 3 logarithms or something like that, we have to change our strategy a little bit. And we also have to involve the good old properties of logarithms. So let's use these once again. I'll take a screenshot here in case we need to walk them down in the notes. And here's our new equations to solve. So the instructions are pretty much the same. We'll solve the equations. We're going for two kinds of answers, an exact answer, as well as a decimal approximation if necessary. Same rounding, we'll go for 2 decimal places on this as well. So this one is kind of weird. There's only one logarithm here, so we can't use the strategy in the previous set of examples. We can't equate inputs to logarithms any longer. That's okay, we still have a good strategy for this. But the very first thing we'd actually want to do here is the following. Isolate log base 5 of 6x squared plus 1 first. So if there's just one logarithm in your equation, like in this case, that's always going to be your best first step. We're going to try to isolate this portion of the equation. So let's start by subtracting 2 from both sides. They'll turn into 8 log base 5, 6x squared plus 1 equals 16. Next, divide 8 by both sides into both sides, and we get log base 5 of 6x squared plus 1 is 2. And now we're ready for the next part of the strategy. In fact, we've used this before, but it has been a little bit of a time. Anyone recall what the next step would be at this stage? It's been kind of a while, so no worries if you don't recall. And it didn't seem like it was important when we were looking at these strategies in the past, but suddenly it's became a big deal. So let's make a comment right here. This is in logarithmic form. The strategy at this stage is convert to exponential form. And that's the strategy with equation solving. We just got through solving exponential equations. We have a huge repertoire for that now. So if we can get this into exponential form, we're pretty much home free. Here's a strategy. We want to look at the base to start. Then 2 here will be the output. 6x squared is the input. So to convert this to exponential, we start by writing down the base. Next step, what was the output, the 2 here, becomes the input to the 5 power x function. So it goes in there. And what was the input now becomes the output. So 6x squared plus 1 goes over here. So finally, that's our new equation. This is now in exponential form. I'll write exp for exponential, just to save a little bit of time. And that's our exponential form. Like we mentioned, we've solved quite a number of these already, even before we started these notes today. And so the strategy is take something that looks esoteric, write it down as something familiar. On the left-hand side, 5 squared is 25, equals 6x squared plus 1. And I mentioned, whenever you see a quadratic equation, you usually want 0 on one side. But you know, that does actually depend on the quadratic equation. This quadratic equation is special because you can isolate the x squared, and you're really isolating x in a certain sense. So this time, let's just isolate x squared and take a square root. Subtract 1 from both sides to get 24 is 6x squared. Divide by 6 and we'll get 4 is x squared. Then take the square root of both sides. But once you do that, there is 2 possibilities. X is going to be positive or negative square root of 4, which implies x is equal to either negative 2 or a positive 2. So the moment we have these answers, no matter if they're positive or negative, we should check them out. Sometimes the positive number could be the extraneous solution, the one that doesn't actually work in the equation. Sometimes it could be the negative, sometimes it's both or neither. We have to take a look and see if they work. So we'll start with that negative 2. If you plug a negative 2 right here, I'm going to check it on this equation where we isolated the logarithm. Negative 2 in the input will be 6, negative 2 squared, plus 1. That will give us a value of 25 altogether. So log base 5 of 25 equals 2. Let me write over here on the margin. That right there is a true statement, because 2 is the exponent that 5 must be raised to in order to get a 25. Or just convert it to exponential form, it would read 5 to the power of 2 equals 25. I definitely believe that statement, so this -2 works. No problem with that one. Then we do it again. Plug in the 2. That power of 2 is special. It means it's probably just going to work as well. Plug it into 2 and it's still 25, whether it was positive or negative. So the check is the same. And that means they both work. Those are our solutions on this problem. I'll put a box on them again just to emphasize we found them and they both work. Any questions with that one there, folks? Okay, so if you see one single logarithm, sorry, go ahead.
We said the decimal approximation as was. Yeah, so it's a both. But that's the answer.
Yeah, if it comes out just as an integer, it's both the exact value and the approximation would be like 2.00. So in this case, we would just give the -2, +2. The decimal approximations are more for stuff like that mess right there. It's good to know, well, what is it, that number even? And so that's the ones we're mostly going for. Other questions at the moment? Okay, well, if you have one logarithm, that's pretty much the strategy. Get it in exponential form after isolating it, and you're pretty much home free after that. So let's see what happens in part B. Part B looks a lot nicer. And I'll say it's not too bad, but it does involve a different strategy. So what's happening this time is we have logarithms in 2 spots. Well, 2 logarithms altogether. If there's 2 logarithms, well, we might try to use the equivalence property. That doesn't work because of the +4 here. There's no way for me to write this equation in this format, in other words. We could have written it as natural log 5 equals natural log x minus 1. We would have said 5 equals x minus 1, and we're home free. 6 equals x. But that's not our problem. This 4 here is destroying that strategy. I can't put a logarithm isolated on the left side and another logarithm isolated on the right-hand side. So that means we have to do something else. And that something else is somewhere inside here. Anyone see a good property that could help us out? Good call. It's absolutely property 5. We start with the right-hand side where things are being added together, and then we consolidate down to a single logarithm. That's the strategy we were practicing on Tuesday's class with properties of logarithms. Going in this direction, left to right, is for now equation solving. So we're going in this direction. Up here, this will turn into natural log of 5 times x minus 1 is 4. So with that one step, we're now home free. It's one logarithm. We can convert it into exponential form, maybe after simplifying, and this will be solved in pretty short order at this stage. So just for the sake of comparing what happened here, think of this 5 as playing the role of x. And think of this x minus 1 playing the role of y. Then all that happened was we took the x, which is 5, and we took the y, which is this x minus 1, and just multiplied them together. So that's pretty much the idea of this whole step here. Let me copy that down just in case we want that color coding again. Now, at this stage, you can get pretty fast to what you want to get it in exponential form. Let me simplify this a tad. Natural log is just fine the way it is, but it hides your base, which is base e. So sometimes this is not a terrible strategy. Write this out as log base e. That is still the natural logarithm. Let me highlight in yellow just to emphasize. The input is 5x minus 5. Just did a quick distribution side there. Equals 4. At this stage, we're just going to convert it to exponential form, and here's how it goes. Start with a base always. That's a good strategy here. The 4 on the right becomes an exponent. 5x minus 5 on the left becomes the output. So now that's our equation to solve. And e power 4 absolutely looks weird, but it's just a number. In fact, if you put in, say, e, that's about 2.71. E power 4 is 54.60 roughly. So it's nothing really special. It just looks funny on paper. We're solving for x, so the next step should be add 5 to both sides. So e to the power 4 plus 5 is 5x. Next, to solve for x, just divide by 5, and here's our exact answer. X equals e power 4 plus 5, all of which is divided by 5. And next, we'll just need an approximation of this quantity right here. We did it, folks. I feel like this one is definitely pretty tricky. If there's multiple logarithms, we have to now consolidate them, is the major idea here. Well, back to the calculator. This one's kind of tricky to put in. You will want to start with a parenthesis that e power 4 plus 5 if I can get this to work out for me. There we go. Plus 5 divide by 5. This is what it would look like in Desmos. And it would round to 11.92 altogether. I feel like this one is definitely a tougher approximation. Any questions on getting that 11.92? Oh dear, can I see what it looks like on the input? So, oh weird. Well, you would want to, for the approximation, we're really just approximating just the e power 4 plus 5 divided by 5. And so for just that portion, you should be getting 11.92. But other questions at the moment so far? Okay, well, that's another equation down. And these ones are pretty common, actually, I'd say. There's going to be plenty of exercises in the WebAssign where this kind of strategy has to be deployed in order to get the answer that we're going for. Let's try it again. Same kind of stuff on part C next. We have a log base 3 this time, plus a log base 3 of x plus 6. Because of the plus in the middle, we're just going to use property number 5 again and consolidate everything. So we have an x at x plus 6. And first step on this one, we can write out log base 3 of x multiplying and x plus 6. So that whole thing is set equal to 3, and that means we're pretty much home free on this one as well. What we do is take the base here. Let's convert this now back to an exponential format. I'm going to highlight this 3 since I see a matching 3 over here just to show the pattern. So 3 comes down, but it's the 3 that's the base to the logarithm. This 3 now becomes the input, and x plus 6 becomes the output. So our goal is now to solve this equation right here. Any questions so far, folks, to that stage? Okay, and totally the key step is really right here. I don't know how to approach this equation at all if we didn't take that one step. Without that one step, pretty much anything that I would write down is pretty much going to be just some weird attempt spinning my wheels trying to get some answer out. But without this, we're pretty much lost trying to get through it. This stage, we have a quadratic equation. 3 power 3 is 27. Distribute x into the right-hand side, and we've got an x squared plus 6x. And this is one where isolating x squared is not going to work. 6x is the problem. We need 0 on one side. We'll try for a factorization and quadratic formula if it's necessary. So 0 is now equal to x squared plus 6x minus 27. That one doesn't look too bad to get through. We'll have 0 times 2 groups, x plus and minus. And if it's at 27, 9 and 3 is a good choice. Let me double check that one. Here to here is negative 3x. Here to here is plus 9x. That would give us 6x, which is a success. We were going for that. We have the right middle term. So that means the factorization did work. Then this next implies x plus 9 is 0, or x minus 3 is 0. That's the only reason we want to factor it, to split into two equations. And both are pretty much just immediately solved. X is negative 9 here, positive 3 here. But once we get here, there's some problems. Question over here or comment? Good call. Right from here, we have a domain condition. X has to be bigger than 0 in interval notation, 0 to infinity. You can't take the negative 9 and plug it into this original equation, in other words. And even if we tried, it'd be something like this. I don't know how to put log base 3 into this calculator, but it would be any logarithm that would be a problem. Let's say log base negative 9, just purely undefined. So watch out for those kinds of things. Negative 9 doesn't work on this one. We have to check it. So this one's gone. But we should be just as suspicious with 3. It's not just the negatives that cause problems. Sometimes a positive value will. So if we plug a 3 here, that's not a domain issue. We're okay. Plug a 3 here would be log base 3 of 9. That also works out. So I think we're in great shape with our 3. We can say x equals 3 is our answer. Weird instructions, I know, because this one doesn't have a sensible approximation. That's the exact value. So we'll just leave it right here as our answer on that one. Well, any questions, folks, on the solution here? Okay, so pretty much, again, the properties of logarithms are vital to just about every single equation we solved here, except for a few at the start of the notes. And so these are always going to be something that they'll be provided on the final exam, but having them available is not the same as being familiar with them and having practiced using them. So that's what we're trying to get through today, so that we'll be in great shape when we solve these in a final exam type setting. So here's our next one to give a try. And this one's kind of rough. Anyone see what makes this one a little bit different than before? There's a couple issues, right? This time there's 3 logarithms, 1, 2, 3, whereas before we were dealing with 2 and we just consolidated them. But there's yet another issue with this one that makes it kind of different from all the rest. Anyone spot what the next difference is? Good call. The negative sign there is actually really tricky all of a sudden. We might expect pluses in the middle, but that's no guarantee at all. And if there's a negative, property number 5 is out of the question. We're using property number 6 only because of that negative sign right there. So here's how that property is going to go. Let's work it out carefully. So I'll think of y as being the 5 in our problem, and I'll think of x as being the x minus 4 in our problem. The x stays put right in the numerator, and the y gets chucked down into the denominator due to the negative coefficient right here. So this converts to log base 7 of x minus 4 in the numerator, divide by 5 in the denominator, equals log base 7 of x. So now we've got it, folks. It's now 2 logarithms, one on the left, one on the right. But this is a really good place to be in. Let me scroll up for just a moment to highlight what we're about to do. Whenever you have 2 logarithms and they're at one side of the equation or another, this is absolutely what you would want to do next. We're just going to take the inputs and equate them to each other, now that we have something of this format. So back in our problem, the things that we're going to equate is x minus 4 divided by 5 is now equal to x by the equivalence property of logarithms. So this implies x minus 4 fifths is now equal to x. That's not a terrible equation to solve. We can multiply both sides by 5 to start and then just go through the motions. But any questions, folks, on getting through the first 2 steps here? Okay, so once we're here, back to this side, if you multiply the left by 5, you'll get just an x minus 4. and the right-hand side will turn into a 5x. Then I guess we can subtract x from both sides. -4 is now 4x, divide by 4, and -1 equals x. But you never ever want to celebrate too soon on this kind of stuff. Anyone see what we should say very next? Exactly. After all this trouble, all this careful work, and we didn't make any mistakes in our work, this just doesn't check. From right here, we have a domain condition where x has to be bigger than 0. And so we have 0 to infinity as valid results. So -1 has just gone. And like you said, the only statement we can make is no solution. It seems kind of not satisfying to work through an equation carefully, especially a tricky one, to get that as a reward, but it can happen. We did it, folks. That's several strange looking equations. And these aren't the kind of equations you would see for solving the applications we're going to start taking a look at next. But any questions, comments at the moment? Okay, well, before we go to the next section, we're really going to do that on Tuesday. The next bit of the notes is kind of like a segue. There's two extra examples we want to take a look at, but really their whole purpose is just get familiar with taking this information so we can write down an equation, and whatever that equation looks like, we'll use the strategies up above here to solve that given equation. So think of everything up above as the method, and examples 5 and 6 is the purpose. This is the reason why we're trying to solve any one of these equations. Let's start off with Gina. Whoever Gina is depositing $6,000 into an account with 2.35% interest rate annual, compounded quarterly. If you saw that information, I'd say a good first step would be organize. The principal amount invested is $6,000. The interest rate we're going to use is R, 0.0235. This has to be converted into a decimal. And when it says compounded quarterly, that means there'll be n equals 4 compoundings. Next thing we'll use is, let's put down the formula for compound interest. Keep in mind that one is on the formula sheet that will be handed out for the final exam. So it'll go A equals P times 1 plus, oh, that is a mistake there. Let me try again. 1 plus R divided by N, not the other way around, times NT. It's a good idea to just put this down on paper first. And even if maybe for some reason you just ran out of time, this is a good amount of partial credit already. You're showing your understanding of the problem, and this is the direction you need to go. Next, start filling in values. A is equal to 6,000 for the principal amount. 1 plus the interest rate, 0.0235, divide by 4 to the power of NT. So pretty much all I've done is taken this information and wrote down an exponential function that models that information so far. Yeah, go ahead. Oh, thanks for spotting that. That's a 4 right here. So 4 in that location. Thanks for seeing that, Justin. Other questions so far? Okay, now the next part of the problem says, assuming no withdrawals are made, how long will it take for the investment to grow to $500,000? Seems like a fun question because $500,000 is a decent change still even these days, but the interest rate is very, very puny. So we're expecting a very long time. The person's probably not going to survive to see $500,000, but they're only investing $6,000 once and they're not putting in further investments. So it seems like it should be a long time. We'll take that 500,000, and this is the new element of the problem. This is what goes right here. We want to solve for the time t that will result in $500,000 for the amount in the account. So 500,000 on the left is now equal to 6,000. Because we're solving an equation this time, good idea to just shove all of that into a calculator. But watch out for this in the instructions. I copied it verbatim for Alex. Alex wants a pretty accurate answer. So they're asking us not to run the computations in the middle, only your final answer to land on that accurate answer. So over here on the calculator, 1 plus 0.02 3/5/4, I have to carry in all of those digits. And because the equation is exponential, they really matter. Leaving off some could make it inaccurate enough that we're losing values in the final answer. So it's 1.005. Didn't make that parenthesis large enough. 875 to the power 14. And honestly, this is what you would want your bank to do, right? As well, right? You wouldn't want your bank to round that number. You'd be leaving money on the table. You want the most accurate expression possible right there by the red dot. So now to solve this next, let's take the 500,000 blue, divide by the 6,000. And we're getting 83.3 repeating. That would be 83 1/3 if we wanted the exact answer. Or we could just write this as 500/6. That would be valid as well. All I've done is not a great simplification, but I've just canceled these zeros like that. If I can get it right, there we go. So we have 506. Then back over here, this is now just the 1.005875 to the power of 4 times t. We're looking for the time in years to get to that 500,000. So the next thing we need to do is that variable t, it's in the exponent position. It can't be there. We have to free it up. This is where we use logarithms, and the natural log is a good choice. Take the natural log of the left-hand side. Take the natural logarithm of the entire right-hand side, and here's what we get. And the only reason, again, that we use this strategy is that that entire exponent on the next step will turn into a coefficient to the natural logarithm. That allows us to finally really solve for t. In fact, we're only just a couple steps away. Any questions to this stage so far? Okay, let me write in that next key step. We have the natural log of 500/6 equals now a 4t in this step. That's an important step, so I guess it deserves that color. Times the natural log of 1.005875. And because we're solving for t, we're just going to divide by the 4 times that natural logarithm into the left-hand side right here. So it'll become natural log of 500/6. On the right-hand side, we're dividing by 4, so it emerges here. We divide by this logarithm, so it's also down here. And the right-hand side is just t. So that's our exact answer, and we didn't round a single thing. We kept every digit along the whole entire process. But now we're ready to round our end answer to the nearest 100. Any questions to that stage? Okay, so from here on out, it's just an adventure in the calculator. T is going to be equal to, remember the interest rate is really bad, and we're going for $500,000 somehow. That's really kind of impressive thinking. Let's see how long that'll take. Natural log of 500/6. Right now it's saying 4.42 years, but we haven't divided by the right thing. 4 times the natural log of 1.00. It's undefined because natural log 1 is a 0. I'm dividing by 0 at the moment. Once I put in the 5, there we go, 5. We're up to 221 years. Put in the 8, 191 years. 7, 188. 5, 188.75. Every one of those digits actually matters. It's impressive to see the answer change as you put them in. Let me double check I got them in right. Okay. So it will take 188.76 years. Which is definitely a pretty long time. But we did it, folks. That's modeling and finding a time to arrive at a certain amount in compound interest. We'll see a lot more of these kinds of equations in the next section notes. But any questions at all getting through that one? Okay, let's let's try out one more for the road. This next one is pretty quick to get through, and then we'll call it a night. Once we come back on Tuesday's class, our whole objective is just to work on section 6.7. I put a lot of problems into that one, so we might not hit every single example. Whichever ones we don't complete, I will put in the full solutions too. But let's treat this as our last example for the night, for the day. This is not a night class yet. This one is a modeling type problem that comes from Newton's law of cooling, if you're curious about this one. It says a bottle of water is placed into the side of the refrigerator. As the water cools, its temperature, C at T, looks like it's in Celsius, is given by this function. So this is going to tell us the temperature at time T for this bottle of water. T is number of minutes since the bottle was placed in the refrigerator. And we want to know how long will it take for the bottle of water to reach a temperature of 14 degrees Celsius. So we're just going to throw 14 right there. That's the temperature at any time T. Set it equal to the function 5 plus 13 e to the negative 0.029 T. So now that's our equation to solve here. And again, it's really not too bad. There is one exponential function in this whole equation. Our goal is to isolate it, and then we'll take the natural log of both sides. So start by subtracting 5. 9 is now equal to 13 e to the negative 0.029 T. Next step, divide by 13, so that 9/13. Give it a little bit of space around the equality, and a little bit of space on the other side, e negative 0.029 T. Reason for all that space is, the immediate next step is, I need to take this T out of the exponent position. Logarithms always work, and this time the natural log works exceptionally well, because there's a cancellation that goes that way. We don't even have to try to bring down this from the exponent as a coefficient. Everything here is just completely gone. The right-hand side is negative 0.029 T. Left-hand side is natural log of 9/13. And that means final step is just to divide by negative 0.029 T. So the end step is T equals natural log 9/13 divided by negative 0.029. On paper, this looks absolutely wrong because we're looking for time, right? And that looks like a negative number, but it's actually not negative. Logarithms are just tricky when you look at them. This is part of the reason why looking at graphs of natural logarithms or any logarithm is pretty handy. The graph of the logarithm looks like this. It always intercepts the x-axis exactly at 1. But if you put in something like 9/13, you're right over here, and you get a negative answer out for the natural log. So even though it looks funny, you have the right answer at this step. We just need to trust it, put it in the calculator. So here's how it would go. Natural log 9/13. Just putting in that much, we can observe, yes, it really is negative. So we're in good shape because we're also dividing by negative 0.029. Then the final result is, let's see, we're going for, it never specified rounding. Let's just try for the nearest 100, 12.68 minutes. So kind of a weird problem. If you ever take your bottle out of the refrigerator and want to know how long it takes to cool down to 14 degrees, that's the answer, 12.68 minutes. Well, any questions, folks, with solving that equation there? Okay, well, that's the wild adventure of solving exponential logarithmic equations. When we come back on Tuesday, again, it'll look very familiar to what we just did on example 5 and 6. We're just continuing forward with these kinds of questions. Well, any questions before we call it a night? Okay, have a great night, everyone. And I'll be in the tutoring room as usual if you have any further questions. But question over here, Michael? Gotcha. Oh, I see what you're saying.